So what does the Pythagorean theorem tell you? Pythagorean theorem tells you that if you have a right triangle, so if this angle is 90 degrees, the connection between these numbers is what? A squared plus b squared is equal to c squared. Big question. What if the angle wasn't 90 degrees? What do you have then? So let me say the what? Law of cosines. Yeah, we have law of cosines to handle that problem for us. So let's take the following picture. Let's say this is A, this is B, this is C. Or let me just to write it in the way. C. Okay. Let's say this is angle theta. So the side C is not necessarily opposite a right angle, but it's opposite some arbitrary angle. The question is, what's the connection between length of this side and the information you got here between A, B, and theta? What does that tell you about C? So 2AB what? Cosine theta. Okay, how do we get that? That's magic, yes. Nice magic. Okay, well, all such problems, they have to be reduced to Pythagorean theorem. So we are going to go back, quickly visit stuff from geometry way back when. So I drop a perpendicular to create my right triangles. Okay, so that is divining this thing. We have this this right triangle being created by this line. Let's call the length of it h, and as a result we have created this two length here. Let's call one of them x, the other one y. Now we need a tiny bit of basic definitions in trigonometry as well. So let's go here and practice this. If this angle is theta, and this is a right triangle, and we are calling this h, here we're calling this x, and this guy is a. What's the definition of cosine of theta in this picture? Adjacent over hypotenuse, which tells me x is equal to, so adjacent is equal to what? Yeah, hypotenuse times cosine. Similarly, sine of theta is h over a, which tells me opposite is equal to a sine theta. Well, that is exactly what I need here. This x that I got, this x is a cosine theta. This h is a sine theta. So who's going to be y? If the whole thing was b, this much of it is reserved for x. So this is going to be b minus x. Is that right? Okay. Now we are going to focus on this right triangle. In that right triangle, apply the Pythagorean formula for me. What does that say? C squared is equal to h squared plus y squared. Now let's for a moment instead of y just write what it was. It was b minus x. So hopefully you remember how to square stuff. B minus x squared, what is that? B squared minus what? 2bx plus x squared. Now let's remember who everybody was. C squared is equal to h. Who was h? A sine theta. Is that right? H was a sine theta. So this is a sine theta squared plus b squared minus 2bx. Who was x? A cosine theta. X was a cosine theta. And again, who was x? A cosine theta. So c squared is equal to, squared is a squared sine square of theta b squared minus 2ab cosine theta. Square of that, a squared cosine square of theta. What are we going to do next? C squared, we say, pay attention to these. What's a common factor between the two of them? A squared times sine square plus cosine square of theta plus b squared minus 2ab cosine theta. And then who's this? What is sine squared plus cosine square of an angle? 1. Okay, so that's basic trig identity. That again is same thing as the Pythagorean theorem itself. The fact that this is true is exactly the same as this is 1. So c squared becomes a squared and then b squared minus 2ab cosine theta. So this is what you refer to as law of cosines in geometry or trigonometry. Okay, so something like that shows up in your pre-calculus somewhere. That
possibly need to derive that?
no, you don't. So this is a way of measuring the angle theta. That's what they use when you do land surveying or something. Well, the machine usually does it for you, but some years back you didn't have the machines. Actually, somebody had to do this. If you have the length C and you have the length A and B, how do you get the cosine of theta out of here? So you can say cosine of theta. Let me rearrange this. I say 2ab cosine, I brought this to this side, is equal to a squared plus b squared minus c squared. So if you want angle, for example, you could calculate it out of such a formula. You might have done this back in your trigonometry class. Well, what we want to say is this formula that we have here is really a reincarnation of that idea, just in the language of linear algebra. It is really the same thing. Well, let's see, how is it the same thing? Let me redraw this picture. So I have A, B, and C here. This was, so we had this guy was theta, this was A, this was B, and this was C, and this was connection between the two of them. I want to use vectors instead. I say, okay, suppose this is the vector U, and this one is the vector, say, W. How can I make a vector for C? Like, say I want to make this vector for C. What should I do to U and W to get this black vector? Subtract. In what manner? Is that U minus V or U minus W or W minus U? U minus W. Minus W, remember, minus W reverses W, reverse W, and then go along U. So this is U minus W. So, well, what were we doing there? We were figuring out the length of U minus W. So let's do the same thing here. So U minus W, suppose I want to find the length of it. What's my motivation for that? Well, this formula had the length of that guy. That this is really C. If you want to square it, is the square of the length of U minus W. Now, if I have some vector A, what did we say about A dot A? It is same as what? Length of A squared. So U minus W squared is really U minus W times, that is dotted with itself. Well, let's just go ahead and do the algebra. I have to multiply these two parentheses. I'm doing a dot product, but we have learned all the rules of multiplication here are essentially the same as rules of algebra we had. So first with first, but what kind of multiplication? Dot multiplication, is that right? U dot, excuse me. U dot U. What else? Read out the rest of them for me. So first with first, that I got U dot W. Yeah, this times that one is negative U dot W. Now this one times this one, negative W dot U, which is negative U dot W. And last with last, W dot W. Okay. What is U dot U? Remember, this was U. That is U squared or A squared. Is that right? U dot U is the length of the vector U squared. That's just A squared. How about W dot W? That is length of vector W squared. That is B squared. What is left in between? That is minus 2 U dot W. Okay, let's rewrite this thing. What do we have so far? I have C squared is equal to, let me write it, A squared first and B squared minus 2 U dot W. What did we just discover? We discovered that C squared is A squared plus B squared minus 2AB cosine theta. What do we get out of this? The U dot W, yeah, this is equal to this. Now that style of multiplication was based on the definition of dot product with the component notation, that is U1 times W1 plus U2 times W2 plus U3 times W3. That is same as on the right hand side, A is the length of U B is the length of W and cosine of theta is just cosine of the angle between the two of them. So the formula that we are introducing is simply stating Pythagorean theorem. It just looks a lot more sophisticated than the Pythagorean theorem, but it's really the same thing. So to say that U dot V is equal to the length of U times length of V times cosine of the angle between the two of them, or sum of the product of the corresponding components, is all the same thing. Okay, so now let's move on to a major application of this concept. And that's the idea of projections. Okay, so what I expect you from you to know from what we just talked about is to figure out either dot product or the angle between two vectors. The proof that we just gave is more like a icing on the cake. Idea of projection is the following, that in many applications you have two competing vectors to consider. Like you have a vector W and a vector V and a vector W. Sometimes you might be interested in dropping a plumb line or perpendicular from here to the other one. So you're dropping a plumb line from here to the green one, and for whatever reason you might be interested in this. We call that P. P, for example, projection of W on V. So P itself is a vector, is this black vector, and W is that blue one, and V is that green one. Sometimes you are interested in figuring out this P, sometimes you are interested in figuring out this red one, all sorts of application. This is called the normal component, this is called the tangential component, and such. Okay, we want to have a simple formula for P, and then to use it in the context of projections. We need two simple ingredients. One is the following. If I have a certain vector, let's call this vector A. Say I want to make another vector in the same direction as A, but of unit length. So I am calling it unit vector. So perhaps this A is a long vector and I want to cut it to size, make it like a standard yardstick. What should I do to A to get this unit vector? So let's call this U to be unit vector for me. So suppose A has length 5. What should I do to A to cut it down to size? Divide it by whatever its length is. So length of a vector is given by this notation. Name of a vector in absolute value notation, or as we said in the book, they use double vertical bar, but I don't want to make it crowded here. So to get the unit vector, you simply divide that vector by the length of it, and then you are all set. So that was simple enough. Second thing, let's go ahead and, well, just for convenience of creating our formulas, let's call this angle theta. Now I have this right triangle here. Let's call this side A, call this side C, and this guy B as usual. What is A equal to in terms of C and a trig function of this angle theta? We said it's C times, let me refresh your memory. Cosine of an angle theta was adjacent over hypotenuse. So if I turn it around, the adjacent is equal to hypotenuse times cosine theta. Now, this A is the length of this vector W. So let's use the proper notation. Excuse me. This A is the length of the vector P. C, hypotenuse, is the length of vector W. And then I have cosine of theta. I say, okay, I want to bring this quantity V into my picture to create a formula that starts with W and V and ends up with my P. So what do I remember? I say I have ingredients of a formula I just saw. I take this thing, multiply and divide by the length of V. Let's see what's the use of making our life more complicated. It looks like I multiplied and divided by V. Now the numerator of this fraction is something familiar. Let's look at it. It's the length of V times the length of W times the cosine of an angle between V and W. What was another notation for the same thing? That dot product of which two vectors? V and W. Who is the denominator? Denominator is length of V. So one thing I got here already, I've got one formula, which is length of the projection, length of projected vector P is equal to, this is just the length of it. What is it? V dot W over. Now how about the vector P itself? This is the length of it. Let's go back to this definition we had here. A unit vector is a vector itself divided by the length of it. If I have the length of a vector, how would I find the original vector itself? Say if I want to get a vector A, I can take the length of it and multiply by the unit vector in its own direction. So here I come and say the vector P that you want to make, this vector P, take the length of it, here's the length, multiply by a unit vector in its direction. Well, the unit vector in the direction of V is just V divided by the length of V. Everybody follow that? Became a bit complicated. So this is what I multiplied with is the unit vector in direction of V, which is most often just direction of P as well. Now let's rewrite V dot W. Now length of V times length of V. You can write it as length of V squared. And here's your vector V. Another way of writing same thing is V dot W. Length of V squared is same as vector V times vector V. And then here we have another occurrence of letter V. So let's write what we got. This is projection of W on V. Okay, so remember what we got here. Those of you who want to go further, you have to learn how to reproduce the proof for yourself. But right now, we are here as a looking for application of math. What you need is to see how to apply this particular formula. Let's go ahead and take a simple example. Suppose here I take a problem problem 42. It says U is given as 3, 1, 3. V is given as 4, 1, minus 2. Question is compute the projection of U on V. So you have some U, you have some V. We want to know what's the projection of this on the other one. And what we are after is the vector projection, not just the length of the projection. So what do? You help me out to figure this out. Here is the formula. If you are projecting on a certain vector, then it is that vector that shows up 4 times in your formula. Okay? So this is like where the shadow is being cast. The shadow of U is falling on V, and you want to figure out what that shadow is going to be, the length as well as its direction. It is this vector that shows up 4 times. 4, 1, minus 2. You have to dot it with, well, 4, 1, minus 2, dot it with itself, or find the length of it, dot it with what in the numerator? 3, 1, 3, and to get an extension or to get a direction to this vector, you have the 4th round of appearance of the same vector. Okay, from now on, here is downhill. What do? help me out in the denominator. Remember, when you multiply these things, everybody gets squared. Don't get confused with the negatives. So 4 times 4 is 16, and 1 is 17, and what else? What's the total on the denominator? 21. Okay, minus 2 times minus 2, don't get sidetracked there. It's going to be all positive here. 21. Numerator, we have 12 plus 1 is 13 minus 6. So what is the total on the numerator? 7 times. So this one simplifies to 1/3 of 4, 1 minus 2, or if you wish, 4/3, 1/3 minus 2/3. So what is the meaning of this problem? Meaning is that after you cast the shadow on this, and say let's call it P, or the book is calling it W, or whatever, this projection has what relationship to V? Is 1/3 as long as V. This is the magic factor that came out. Your projection of original vector on the second vector turns out to be 1/3 of that place that you're projecting on. Okay, we were still short of one major idea in this section 3.2, and that's so-called Gram-Schmidt process. Those are the problems that are coming toward the end of this book. It's a very important idea in engineering, actually, but you have to postpone it to next round. So for today, you want to figure out the problems from 31 through 42.